biomedical image processing course. Today we will see the morphological transformation which we required for the purpose of feature extraction and enhancement. So how it is used in Python and OpenCV is our objective of this today's talk. The basic idea of erosion is just like soil erosion only. It erodes away the boundaries of foreground object. Morphology transformation implemented in Python using these group of steps. Some inbuilt functions present that we will see in this set of codings. So we need to import CV to import numpy as np, then use a user defined variable to store the image which we retrieve with the help of imread function, then form a kernel which is np.once of size 5 by 5, then use erode function. For that a statement is cv2.erode followed by the input image, kernel and number of iterations. Then to display the input along with erosion version output of the image used IamShow function, so it will display the resultant image. For example, here we have an input image to the left side and right side one is the output after erosion. Using erosion, overall we will thin the object. By thinning it, due to thinning process, partial connection becomes separate. So our objective is to make the connected object separate so that each individual object can be further processed. For that purpose, we will use the image morphology transformation called erosion transformation. Next one is dilation. It is just opposite of erosion function, and in that what we do is we will make the object thicker, and due to this thickness partial connection become strong joint. So for the purpose of to make the object strong joint, we used to apply the operation called dilation. Here we have a group of statements, set of statements to perform or demo the input image with dilation function. Main function is cv2.dilate. This function has a parameter like take a input image, take a kernel, in this case it is 5 by 5, number of iteration, and then get the output which is dilated. Lastly, some group of statements are written to display input image along with the output after dilation. Now here if we see an input image to the left side as compared to it, right one which is after dilation has thicker edges, and due to this thickening the partial connection become strong joint. We can use it to fill valleys between the object, which will use to fill the holes appear on the image surfaces. These holes can be filled with dilation operation. So multiple applications we have of the dilation. Now erosion and dilation individual are used for thinning and thickening respectively. Now combination of these two can also form new version of morphology named as opening, which is just another name of erosion followed by dilation. So sequentially if we go of erosion and then dilation, it's become opening. It is thinning the object followed by thickening the object. Due to thinning, we separate two partial connection, and to recover their original size, we have to go for dilation. So combined together, we have an opening in which partial connection becomes separated and we get original shape and size of the object. It is useful in removing noise also. the function used to do this opening in morphology named as CV2.morphology x as the name of function for opening. Now we'll see an example to see the demonstration of the opening in morphology, in which numpy is necessary to be imported. Read the image, then form a kernel. This kernel is of size 5 by 5 and the output will stored in the kernel, in which the elements are 1, because function used to create the kernel is np.ones. So it will give the output in the matrix as ones in the required location. Then the function is cv2.morphology.ex having parameter input image and cv2.morph open kernel. So it will apply that kernel on input image with respect to opening features of morphology and give the output, in which we have separated object with their recovered original shape and size. Finally, output is displayed in single figure window with dividing that into multiple quadrants by a function subplot with size and index number are their respective parameters. The output on the fish image after opening is shown to the right side. If we carefully observe them, we can able to see the effect done after a morphology named as opening. Next one, opposite of opening is called closing, which is reverse of the opening, in which dilation followed by erosion sequence we follow. So first we thick and then thin. During thickening, partial connection becomes strong joint. Then to get their original size, we have to do thinning using erosion. So it is useful in closing small hole inside the foreground object, or small black points appear on the surface of the object. These are their applications, examples to use the image closing. From matplotlib, import pvplot as plt and then also import numpy. Read the image, form a kernel of size 5 by 5 with one placed in their respective location, stored in user defined variable named as kernel. Then go for cv2.morphology.ex having a parameter input image and morphology type close. So using the selected kernel on the input image, it performs the closing operation and get the output where we have the object separated followed by recovered with their original size. Then in this slide we have a function used to display the input, output along with their respective titles in the single figure window, where this slide highlights how fish input image has been processed through a morphology of type closing and we get the output image. This way we process their sequences. Now we will extend this step for age detection. For age detection, a special type is Canny. These inbuilt function present in OpenCV. Here age detection is the method used for extracting prominent significant features from the image. It will use cv2.canny as the inbuilt function to apply Canny Edge detection technique on the given input image. Now we will see a group of statements one by one to apply the Canny Edge detection on input image. Like here, begins with importing necessary packages in the file of a program then read the image, form edges with the kernel of Canny. So CV2.Canny will apply Canny operator on the input image which is currently saved in img variable, and then output of input and Canny will be displayed in this respective set of another successive statement. Like here, a input image and output generated by the Canny. So it will go through, scan through the input image one by one, and finally kept only the edges which are prominent and necessary to get the image features output generated by Canny operator. Then we have next step or most important function in Python is histogram, which is one type of plotting operation. Matplotlib comes with histogram plotting function. Matplotlib.pyplot.hist is the function used for the purpose of to get histogram of the image on the display device. This histogram gives the information that range of grayscale value and its respective count. From this histogram, we can classify the image into dark, bright, low contrast and high contrast. In addition to this, histogram also help us to get the information that what can be a threshold between two uniform region, so that using that threshold we can able to partition the image into their different groups. And using histogram, it is easily possible to get the information of distribution of the image, which type of pre-processing necessary for enhancing and feature extraction of the images and so on. So that's why it is much more important step required for the processing of images, and in Python we have inbuilt facility. With the help of that, we can plot the image into that particular format. From matplotlib we need to import pyplot as a plt, then read the image. Then we have plt.hist in bracket parameters to plot the image according to their distribution, and finally display that histogram on the figure window. So these are group of statements necessary to read and show the image along with its respective histogram. For example, here we have an input image, and to the rightmost side of immediate to it a histogram of that image. It has displayed the range of grayscale value on one axis, and on vertical axis we have a count of respective grayscale value. So it is basic step necessary for doing the image analysis process. While displaying the histogram, we have certain intermediate types too, like number 1, BGR plot. From matplotlib we need to import the package, then read the image and form a variable named as color, which are having a parameter of BGR with blue, green and red. Then have a iterative steps called for, which start with the column in enumerated format. Then histr equal to call chist, which will take input image and some other parameter to generate the histogram. Now to display that on console, use plt.plot function, which will display the histogram of the image on the output device. So using this group of statement, it is possible to perform the image read followed by show its respective histogram, so that we can do the image analysis. Like here, an input image which is of type color, and immediate to that we have a histogram showing the contribution of each basic color distribution in the input images. Histogram equalization is the next step in Python, and OpenCV used to have the normal distribution, uniform distribution conversion of input image. If input image is dark, bright, low contrast, then these three category need to be uniform, and for that purpose we apply histogram equalization. This will convert this three category into high contrast, where high contrast is always good for appealing to human being and also good for automation purpose, because it carries all significant information which are higher group of gray level values, and due to that prominent information we can able to extract from the images. For equalization in OpenCV, we have a function named as cv2.equalizedHist. Its input is just a grayscale image and output is our histogram equalized image. Through equalization, we make uniform distribution of the images, and for that need to import NumPy, then apply matplotlib through pyplot, then read the image and find its histogram. Once we get a histogram, have a normalized distribution using that histogram equalization and display the image along with its input in the figure window, so that we can able to show their respective image with their histogram as shown in this slide. Input image and histogram equalized version. Next step is discrete Fourier transform. Fourier transform is used to analyze the frequency characteristics of various filters. For images, 2D discrete Fourier transform, or sometimes called DFT, is used to find in frequency domain. Let us see the code required to apply this Fourier transform. Here we will use to read the images. Then cv2.dft is the function to create variable for applying discrete Fourier transform. Then we have np.fft shift function to apply the actual Fourier transform on the input image. After applying, we get the output version of Fourier transform. Then display original along with the Fourier transformed output. These group of statements used to perform that particular task. And similarly, like in other output, here also it will break the image into quadrants, and each quadrant display input as well as processed image. This way we go for subplot images. Now here it shows the input and output after performing Fourier transform. So magnitude of the spectrum is shown in the right side images. Inverse discrete Fourier transform is the next step, which will opposite to a discrete Fourier transform. To apply this function, use cv2.idft function on OpenCV to perform the inverse discrete Fourier transform. It used to remove high frequency content from the input image. For that, we have set up a number of functions to get the inverse discrete Fourier transform. Need to read the image, then apply DFT, then followed by shifting using DFT. We have certain rows and column formation, then create a mask first whose center is square and then remaining all 0. Apply the function np.0 to form a mask, and that mask will operate on the input image. By applying a mask to get the inverse, the DFT underscore shift into mask, it will do the convolution of these two and get the F shift as a complete mask. Apply that F shift on the original image then CB2 dot IDFT to get inverse after Fourier transform, and this way we can get the reverse of it. Finally, we have a statement to display a image on the console with input followed by the output after the inverse spectrum, after inverse Fourier transformation. Next function is Hough Transform. Hough Transform is popular technique to detect any shape if you can represent that shape in mathematical form. It can detect the shape even if it is broken or distorted a little bit. To recover such images, we used to have the function. Now, here the group of statements like to import file required packages, read the image, then have a Canny operator on it, and then finally Hough lines as a function to form its kernel. Apply that on the image with certain parameter with the function named as cos, sine, and so on. So we will prepare now the list of required parameters for the function named as to do the convolution through Hough line. Then use that updated output after Hough transformation need to be right on the storage device. So the final result shown, to the left side we have an input image and right side in this particular slide seems the output after Hough transformation. Various applications are there of image processing in Python. Few of them are automobile driver assistant. In that, lane departure warning we can able to get, adaptive cruise control, obstacle warning, etc. for automobile. Likewise, we have digital photography. For the process of that, enhancement, compression, color manipulation, image editing, and digital camera are their subtype. In subplot analysis, we go for referring and commendatory process, 3D visualization and tracking, sports action, etc. Whereas in film and video editing, special effect can be possible to give to the images in the Python and OpenCV. Image databases are also allowed to process, convert image, retrieval, value, visual speech of the product, face recognition, and so on. Whereas in industrial automation and inspection, vision guided robotic can be possible to implement for inspection system. In medical and biomedical, it is utilized to develop the applications such as surgical assistant, sensor fusion, vision based diagnosis, and so on. In astronomy area, astronomical image enhancement, chemical or spectral analysis can be possible to do in the Python. Extended library of application may utilized for aerial photography. In that also we used to have pre-processing like enhancement, missile guidelines, geographical, etc. Industrial automation and inspection area utilized Python for the purpose of automating the vision guided robotics and inspection system. Such automation can be possible to implement in Python. Whereas in medical and biomedical, surgical assistants, sensor fusion, vision based diagnosis are also been area where we can use OpenCV. In astronomy, astronomical image enhancement, chemical or spectral analysis can be an area where we can use Python with number of extension. Aerial photography is another application for enhancement, missile guidance, geological mapping are their sub areas too. Whereas in robotics, autonomous vehicle management system can be implemented using OpenCV. Now in security and safety, biometry verification using face or iris, surveillance for defense, swimming pool and so on. In those areas, we can implement a good interface for the user in Python. For military areas like tracking and localizing, detection and missile guidance can be implemented. Whereas for traffic and road monitoring, adaptive traffic lights, etc. can be their subgroups. Now, summarize today's talk. Overall, we have seen the basics of Python, various DIP operations. Now we will see how to implement these steps for biomedical images in next successive modules. Thank you.